We present progress on the computational universality of swarms of micro or nanoscale robots in complex environments, controlled not by individual navigation, but by a uniform global external force. Swarms of robots, such as this single-celled organism, can be grown or built in large numbers, but are usually controlled by global forces such as a magnetic field. While the motion planning for one robot may be trivial, the problem becomes complex when many robots receive the same motion commands. In the following, we consider a 2D grid world. Here, we are building a large-scale prototype composed of square plexiglass boards that can be assembled together to form a bigger board. In this world, all obstacles and robots are unit size, and for each actuation, robots move maximally until they collide with an obstacle or another robot. We can use these rules to build logic gates. This is a 3-input OR gate. If at least one robot enters at the top, one robot will exit the bottom. Additional robots are recycled to the side. This is a 5-input AND gate. If less than 5 robots enter at the top, no robot will enter the goal location, outlined in gray. Only if all 5 inputs have robots will the goal location be filled. But how can we generate independent choices with global inputs? Here we use a decision tree to set robots true or false. At each stage, the decision only affects one robot. We combine these 3 elements to prove, by a reduction from 3-sat, the NP-hardness of deciding whether we can reach a specific location. Decision trees are used to set each variable true or false. 3-input OR gates are used to form each clause, and an M-input AND gate provides a conjunction. The goal is only reached if the variables are set so that the formula evaluates to true. Therefore, the motion planning problem with global inputs is at least NP-hard. So obstacles make motion planning hard, but obstacles can be a blessing. Without obstacles, we can only move the mean position of a group of robots. No matter what inputs we use, the A remains an A. However, the right set of obstacles enables efficient control of the position of every robot in the group. The obstacles here enable matrix permutations in just 4 input commands. This permutation is an involution, and so by repeating the cycle we can toggle between A and B. Our physical implementation enables matrix permutations in 4 moves. This prototype uses metal and plastic spheres and reconfigurable black obstacles. Our algorithms prescribe where to place obstacles to achieve arbitrary permutations. Here, a clockwise input sequence toggles the position of the first 2 robots, but we can encode a second permutation in the counterclockwise direction. The counterclockwise input sequence increments the location of every robot. Together, these 2 generators enable arbitrary permutations of the matrix, allowing us to bubble sort the array. We designed configurations to implement AND, OR, NOR, and NAND logic gates. However, fan-out gates turned out to be quite tricky. Fan-out gates are necessary for simulating arbitrary digital circuits, such as a half adder. We were able to prove that unit-sized robots cannot generate a fan-out gate. On the positive side, we resolved the missing component with the help of 2x1 robots, painted white in this prototype. These can create fan-out gates that produce multiple copies of the inputs. Using these gates, we are able to establish the full range of computational universality as presented by complex digital circuits. As an example, we connect our logic elements to produce a 3-bit counter. This counter requires 3 fan-out gates, 2 adders, and 1 gate for the carry. We have instructions for wiring logic gates together, and can actuate all gates and wiring by the same clockwise sequence of commands.